Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the steady state response. Yesterday we discussed how we will carry out the steady state response when the input is your non-sinusoidal periodic. So, further we can just summarize what we did in the previous lecture. So, broadly the approaches that has been carried out just to find the steady state response is classified into two broadly. One is the direct phasor approach and second is the spectrum product approach. In direct phasor approach, what we do, we just convert the circuit or network in phasor format and carry out the calculations in phasor, and in the last we just come back to the time domain. It means first the circuit is given the time response or time domain. So, what we will do, we just convert into the frequency domain and all the calculations will be carried out in the frequency domain. In the last we convert back to the time domain. So, this is the approach we carry out in the direct phasor approach. So, in direct phasor approach, the phasor representing response is equal to the product of network function and phasor representing the excitations. So, there are two terms, one is the network function and the other one is the phasor representing the excitation. So, what is network function? Network function is a transformed function defining current and voltages in the different part of the network. So, what it is if the network is in your time domain, so we have to convert it into the frequency domain or S domain, and that is the network function, and the input is also converted into the phasor domain. Suppose the input is given such as, suppose Vt is equal to 20 cos omega t plus 30 degree. This is your input is given. So, in phasor format Vt can be written as 20 angle 30 degree. So, this is the phasor form. So, what we have to do? We have to convert the excitation in phasor form and circuit or network in also the frequency domain. Then we go for the phasor approach. So, let us consider a network function excited by a non-sinusoidal periodic signal. The response current is multiplication of admittance of the network and the input voltage applied to the network. So, this voltage, because the input is your non-sinusoidal periodic, so what you have to do? You have to carry out the Fourier series just to decompose the signal into the fundamental, that is the V1, then you have to second harmonics, third harmonics and Rth harmonics. So, then this current is, this is basically yesterday we discussed. So, this is your I1, this is your I2, this is your I3, this is your I3, I2 and I1. So, this current is calculated. So, this Y1 is, Y is admittance at frequency at fundamental n is equal to 1, omega is frequency of the supply, this is the fundamental component, that is n is equal to 1, this is the n is equal to 2, here n is equal to 2. So, it is second harmonic, then third harmonic and fourth harmonic. So, admittance is a function of omega. So, it will change if the, so for the nth term the current expression can be written as, this is the admittance, this is your admittance and this is the nth value of signal. So, this is the nth component of your current. So, for what you have to, Y is calculated at the frequency of the phasor, which is n omega 0. So, we then further transform the frequency domain to time domain to get the INT, or INT is written as, this is This is your, and this is called steady state response. This is called steady state response. Okay. So, what is the procedure? Procedure is first convert the given circuit into the phasor or in frequency domain, carry out all the calculations in phasor, and in the last we just convert back to the time domain. So, these are the 3 steps. Just we follow these 3 steps are followed. These 3 steps are followed in direct phasor. So, convert the circuit in the phasor, solve in phasor and convert back to the time domain to get the steady state response. This is the one approach. The another approach is the spectrum product approach. So, what we do in this, we use the magnitude and phase spectra of the excitation together with that of the network function. So, network function is given. So, we just take the magnitude and phase angle of the network function, and we also take the magnitude and phase angle of the excitation. So, amplitude spectra of the response is magnitude of the network function and amplitude spectra of the excitation, and we separately calculate phase spectrum of the response. So, which is phase response or phase of the network function plus phase of the excitation. So, we calculate the magnitude separately, take the product of the both the excitation and the network function, and we also calculate the phase excitation of the response by considering the phase of the network function and take the summation of phase spectrum of the excitation. So, this is the approach of direct spectrum product approach. So, yesterday we discussed the Fourier series can be represented in first in the trigonometrical form, then exponential form, and third is the your cosine form. This is the Fourier series representation. In trigonometrical form, exponential form and cosine form. So, in the previous lecture we discussed the cosine form of the Fourier series. Today I am going to discuss take the Fourier series in form of the exponential. So, this is the exponential form of the excitation, and multiplying each Vn by the appropriate admittance, we get this current. This is the exponential form of response. Exponential Fourier series form of response. So, the result may be simplified in cosine form, such as it is equal to a1 cos omega 0 t a2. So, this is the fundamental, second harmonic, third harmonic and so on, by comparing the pair of exponential of same frequency n omega 0. So, this is the way to just get the steady state response of the network when it is excited by a non-periodic non-sinusoidal periodic signal or input. Now, do some problems. So, one problem is like this. It is find the steady state response of series RL network excited by a square signal Vt with omega is given, it is 1 radian per second, whose Fourier series representation is given as. So this is your input, this is your input, and the network is series RL. So series RL is like this. This is your resistor, this is your inductor. Okay, and so value is say 1 ohm and 1 Henry. Okay. Now we have to find the response. So what we have to do? We have to convert. So this is convert into S domain. Okay. So R is independent of frequency, so it will be 1 ohm, and this is 1 ohm, and this is XL, so this is SL. We know that XL is equal to SL, XC is equal to 1 by SC. Okay. So simply we convert into the frequency domain. So calculate the, so what is YS? So YS is, if we take the impedance 1 by ZS, so 1 by ZS is nothing but 1 by 1 plus S. So this is the admittance. Now take the different, so YJ omega 0 is nothing but it will be 1 by 1 plus J omega 0. Okay. Now Y Jn, so it will be n is equal to 1, so 1 by, for n is equal to 1, n is equal to 1 plus 1, so it is 1 by root 2, 1 by root 2, so 1 plus j, so n is equal to 1, so 1 plus j, so it is, then take the magnitude is this, and the phasor is e to the power minus j 45 degree. Okay. So what is, there is n is equal to 1 here, this is n is equal to 1, this is n is equal to 3, n is equal to 5. So we have to carry out the odd harmonics, n is equal to 1, 3, 5. So y j is equal to, here as y for n is equal to 1, for n is equal to 1, for n is equal to 3, for n is equal to 3, y j 3. So y j 3, so it will be 1 plus j 3. So j 3, so what is the magnitude? Magnitude is 1 by root over 1 plus 9. 3 into 3, so it is 9, so 1 by root 10, and angle is e to the power minus tan inverse 3 by 1. So it is coming, if you calculate, this is coming j 71.6 tan inverse 3 by 1. Okay. So it is in the denominator, so if you take in the numerator, it will be minus sign. Then and for n is equal to 5, for n is equal to 5, n is equal to 5, so y j 5, y j 5 is equal to 1 by 1 plus j 5, so 1 by root 25 plus 1 26 e to the power minus j tan inverse 5 by 1. So 5 by 1 is coming, if you calculate it is coming 78.8. So these are the admittance, in phasor, Now I1 is equal to I1 is equal to Y1 V1. So Y1 and V1 is your 1 e to the power, so it is coming 1 by root 2, so it is coming 0.707 and e to the power minus j 45 and it is cos omega t, so it is, so 1 can be written as e to the power j0, so e to the power j0 into e to the power j0, so it remains same. So this is I1. Now I2 is your Y2 V2. Okay. So Y2 you have calculated, V2. So minus 1 by 3 can be written as e to the power 1 by 3 e to the power minus j 180 degree. So this is your V2 for V2. So this is V2. So multiplied with this, so I2 is equal to I2 we have calculated here, this 1 by root 10. So 1 by root 10 is coming 1.105 e to the power minus j 71.6 into 1 by root 10. So it into into j to the power minus 180 degree, because this is basically 1 by root 10 into 1 by 3. Okay, both the components I have taken into there. So I2 is finally I am writing the, just you can check it, it is coming 1.05 e to the power minus j 251.6. So addition of angle of the network function y3 and your v3. Now come to the third component. So for n is equal to 5, it is coming 0.039 e to the power minus j 78.8, because we can calculate for n is equal to 5, V5 is V5, or you can say the V3, whatever it is. So it is 1 by 5 bit. So it is 1 by 5 and e to the power j 0 degree. Okay. So this is the magnitude in the phasor for this is the, so multiply with 1 by 5 and 1 by root 26, we get this value. So this is the, so I is equal to 3 component I1 plus I2 plus I3. Okay, this is for n is equal to 1, this is n is equal to 3, and this is for n is equal to 5. So this is the current. Now we have to, it is in the phasor form, so come back to the time domain. So it can be written as, so in time domain IT can be written as IT is equal to 0.707 cos, it is T, voltage T, so T minus angle of this one, so it is coming minus 45 degree. So this is I1 in time domain. Similarly, for the second component 1.015, this one, then cos 3t and angle this one 251 51.6 plus this one 0.039 cos 5t, okay, frequency, minus this angle 5t minus angle 78.8. So this is the steady state response. This is steady state response. This is the steady state response. So this way we can carry out the steady state response of a network excited by a non-sinusoidal periodic wave form. What is the approach? Approach is convert the circuit into the phasor form, carry out all the calculations, all the current components in the phasor, and finally convert back to time domain. So this is the approach to find the steady state response of a network or circuit excited by a non-sinusoidal periodic waveform. So this is all about your direct phasor approach to find the steady state. So thank you very much. Jai Hind.